asking about electronic spectra, and the terms they are asking, like the E2G that is coming from A to G. Okay, so from this spectra, from this transition they are asking about. Okay, so now our first task is to how these terms arises. So you know that. So in this question they are asking about chromium 3. Okay, chromium 3 complex. So basically we know this is a D3 complex. Now if we take the if you want to find out the term symbol of this ion, free ion, the complex ion, then the configuration is like that. So this is +2, this +1, 0, -1, -2. So these are the ml values. These are the ml values of a d orbital. You know d orbital is a five degenerate orbital. Five orbitals are there. So every ml values are there. So according to Pauli and Popov principle, Pauli experiment principle, we input the electrons like this. So every will be like single electron fill up. Then we'll get the ml as 3. So this indicates basically the F down. Okay. Now for generating the LS coupling, so we take actually basically the 2s plus 1. So this actually comes from the LS coupling. From LS coupling it is coming. So we'll have the S is like the half value is at. We have discussed earlier the spin have half value. So there are 3 odd spins. So total ms equals to 3 by 2. So total it will be 4. Understood? Is coming. So we'll have the S is like the half value is at. We have discussed earlier the spin have half value. So there are 3 odd spins. So total ms equals to 3 by 2. So total it will be 4. Understood? So this is the ground state term. Okay. This is the ground state term. Ground state term. So similarly another terms will come. So if from electron we decide here, then it will give rise to 4p. Okay. Now these are the high spin terms, like the F. When it this F term, when it comes to the crystal field, it splits. So it splits in 3 terms. So every orbital having the F orbital having the degeneracy, you know, at 7. That's 12 plus 1. So L has like the how much? The degeneracy of like 7. So it will split in 3 terms. That is T1G, T2G, and A2G. Okay. Now this is triplet degenerate, this is triplet degenerate, this is single degenerate. So total degeneration will remain 7. You understood now? If sum it up, the total degeneration will be 7. So how actually these terms comes? Okay. So this comes from the high spin. So if we think that there are two T2G and the when the 5d orbitals comes to a crystal field, they give rise to they split into 2 terms, T2G and EG. So T2G had dxy, dyz, and dzx, and this has dx square minus y square, and this has dz square. Okay, so these two kinds they splits. Okay, now when these splits occur, and if you feel the energy, so first is the stablest form. So this is T2G3. So this T2G3 means this is the only one configuration. So it is designated to the A2G term. Now there is another possibility, like if one electron from here it comes to here. Okay. So this has 2 possibilities that will give rise to these 2 triplet degenerate terms. So how are the what are the possibilities? These 3 terms. So what will be the configuration? That is the important thing. So actually F term arises, I told you like it is the high spin configuration. So basically the ground term, this is the T2G3 EG0. Okay. Now these are the excited states. So these two terms they arises basically T2G2 Eg1. So now in Eg orbital we have seen there are two d orbitals. One is dx square y square and another will be d z square. Now interesting fact is that now see how these two terms generate, because it looks like they have same configuration but two term arises. How? So you see now suppose first electron in T2G it comes in dxy, okay, and the second electron means the in Eg if it comes in dx square y square, then there will be more repulsion because two orbitals are in xy plane now, two repulsion. So if in place of dx square y square if the electron comes in dz square orbital, then there will be less repulsion. Understood now? That's why it arises two terms, because the first electron if it first two electron if they are in xy plane and the third electron still appear come in the xy plane, then there will be more repulsion. So that's why that it gives us the high energy. So the high energy comes thus T2 and T1G, the low energy comes T2G. You understood? Okay. That is how this three term generates, and their energy orders like A2G, T2G, and then T1G. Okay. Now when we are talking about P, so P basically how much the degeneracy is? It is the degeneracy like 12 plus 1, so it is a threefold degenerate. So it only gives us a threefold degenerate orbital, it is T1G4. Okay. So to designate it, to distinguish it, we named as a P. Okay. Now when there will be, there is no H term. Okay. So these terms are there. Okay. Understood? Now, so now we learn the Orgel diagram. Okay, Orgel diagram, main formula of Orgel diagram. So Orgel diagram. So what they basically did? So they put the this Russell's 100 terms. So these ground state terms are called due to their LS coupling and JD coupling they occur. So that's why they called termed as Russell's 100 term. Okay. So when F4 comes, so it gives us three energy levels. Okay. So this is the A2G. Okay. 4. So this is T1G, T2G. This is T1G. And another term come P. So due to same symmetry, this they repel each other. Okay, so that's why it goes up. Understood? Now, so this has configuration as T2G 3 Eg 0. This has T2G 2 Eg 1. This also has T2G 2 Eg 1. And this is the first exercise state and this is second exercise state. This T2G 1 Eg 2. Understood? High energy orbital, so that's why they become high energetic. Okay, as T2G has lower energy, so A2G uh, holds in the lower position and T1G holds in the high position. Okay. Okay, now transition can take place from here to here, here to here, and here to here. So basically we expected three transitions. Okay, these are the spin symmetric. So these are the spin allowed transition. Okay, this transition generally appears when we can see these three peaks will be there. Okay, but these are only the high spin configurations. But generally there are also low spin configurations also, and the transition also there. Now see, one fact is that these transitions are broadening. We get the broad transitions. Why? Because you see from T2G to EG, when the electron transfer occurs, basically this gives rise to the change of the bond parameter, because when T2G to EG electron transition occur, basically the delta value affects. So when the delta value affects, it affects the bond, can be contract or maybe elongate. So that's why we get several transitions in the same time, and so the transitions are broadened. Okay, so if there is no delta change, okay, then the transition will be sharp and we will get one peak. Okay, what are the terms? So these are the terms basically. So there are several terms, but these are the like close energy terms. So this low spin now will work. So when this G actually come to the crystal field, this splits in four terms. So what is the, okay? So this gives us to four terms. Okay. So these are basically due to the rearrangement of the electrons. So this is basically comes from the low spin T2G3, but the configuration is like that this will be the configuration. Okay, understood now? T2G3, but the low spin configuration, and then due to the rearrangement, these three terms arises. Okay, and basically these terms comes from the excited state. So how it comes, like T2G actually basically comes due to the lowest energy, and you already know that these terms are high energy as we mentioned. Okay, now we will put all the terms in the one diagram, that is Tanbe sunago diagram. Tanbe sunago diagram. So we will, so here the parameters are little different, So this is like the energy is there, but B is the like Raka parameter. So this B actually gives us the like the separation, the electron repulsion between the terms. Okay. So this is the like Orgel diagram. So in Tanbe sunago diagram, what we did, we place this A to G as the horizontal plane. So if we place it, so you have to rotate it like this. Okay, so you have to rotate it, make it a plane, horizontal plane. So all the thing will rotate. So this is the our A to G. Okay, then T to G will come like this, and T1G come like this. Okay, and when this is a P4 term, so P4 will go above like this. Everyone will anti-clockwise rotation. Okay, Q1GP. So these are F, O, O. Okay. Now comes the G. So G basically split in four terms. So as they are low spin, na. So low spin means there is no electron in the EG orbit. So they are like no such change during the crystal field, because only we have discussed when T2G to EG electron transfer occur, then only delta value will change, and suppose the bond, so they, as they are low spin, so this is the E2G EG. So basically as these three terms only have the T2G electron, T2G3 configuration, so that's why no such change in the delta value. Understood? So they runs parallelly, but A1G has like T2G to EG1. That's why it goes up. It has a high energy value. Now this T2G, now this EG transition. Okay, this we are actually T2G3. So T2G3 to T2G3, this transition doesn't need any high energy electronic field, because you see when you are talking about EG and T2G and the electron jumps from here to here, there is a delta value na. So to overcome this we need this delta value, high energy transition. Okay, but from high spin to low spin during this T2G3 configuration, it doesn't need any energy. It basically occurs in the low energy. Okay, and as there is no bond change, okay, we get a sharp peak. Understood? As you discussed now, when there will be a compression and elongation of bonds, then what happens, the delta value affects. That's why we get several transitions, because when a to g to this transition what t to g, if you consider t1g or t2g, then what happens, the delta value changes like this, then we will get a broad peak, but here we will get a sharp peak. Understood? Okay. And this sharp peak and also actually these are our final region, and this the lower energy, and this actually comes around 650 nanometer angstrom in the visible range basically. In the absorbance spectra, when we are looking for the transitions, then we can find this the lambda. So these are the, so this is basically the T2, the A2G to E2G transition, and this one is the like A2G to T2G, A2G to T1G, and A2G to T1G. This is the P. Okay, understood? So why this is sharp? Because there is no delta change and we get a sharp peak. Okay, okay, and this is around 650 angstrom it comes. Understood? Okay. Another thing that Tanbe diagram is seen, there is the terms are crossing. So terms are crossing means that's not like that, because they are high spin and low spin, so that's why they can cross.